So we're on question activity 1. You see the RC circuit, and notice the switch is closed. So we want to start with the switch closed, and then I press the start button, and once it starts, then I open the switch and I can see it decaying, and it's graphing the decay. And I want to let it go down. It doesn't have to go all the way to 0, so I'm going to stop it now. And we want to get the time constant for this decay. And so the equation for the decay is this, where V naught is V max or V starting. In this case is 1. And we can get the time constant mathematically by doing the algebra on this equation and getting that tau equals T over the log of V over V max over V. And whoops, I got that upside down. So it's the log of V over V max. And so you just take your cursor, I'm not going to do it, but you put your cursor at some point and find out what V max, V naught is. It's going to be 1. And find the time there. And then just pick any other point and find the value of V and the time. And the difference in time goes there, and the value of V goes there, and you can calculate it. But an easier way to do it is just to take the value when t is equal to the time constant, and then you have e to the minus 1. So now put your cursor here, measure, you'll see it's 1 volt, measure the time, and then find out where the value of the voltage is 0.362. So when t equals the time constant, this will be a 1, and e to the negative 1 is 0.368. So that's 0.368 times the maximum voltage, which is 1. And so just bring your cursor down and look for 0.368 or 0.37. Find out what the time is, and the time it takes to get from 1 down to 0.3687, that will be the time constant. And you don't have to use this equation to do the calculation, although you certainly can do it that way. So that's how you find the time constant. You can see if I put the cursor over that starting point, I get the voltage and the time, and then if I follow the curve down until I get the value of 0.37, so right about there, measure the time, get the difference in time, and that will be the time constant. Now you just want to slide this down here to the minimum resistance of 50, do the same thing again, slide it up here where it's 200, and since the time constant is R times C, you would expect in the case of the 200 it'll be twice as long, and in the case of 50 it'll be half as long. That's what you should find. In the next problem you'll see the initial circuit is the same as we just saw, so you want to do what we just did again and get the time constant for this circuit. And then you have 4 graphs of a circuit that has 2 capacitors. All 4 graphs, B, C, and D, they're all the same circuit, and only one of these graphs is going to be correct. So we're looking at the voltage across capacitor A and how it varies as a function of time. So the question is, what should be the starting voltage? And you can see that the 2 capacitors are in parallel. So the starting voltage across each capacitor should still be 1 volt. It's not going to divide like they were series. But we have two capacitors in parallel is twice the capacitance. So how's that going to affect the time constant? I don't want to give you all the answers. I'll let you do this one on your own. Okay, here's the third and last of the problems in Lab 12 that you need to do, because you don't need to do 4 and 5. And you see it's an LC circuit, so hopefully by now you know that's an oscillating circuit. And it says that the capacitor is charged, so the capacitor will discharge through the inductor and charge the inductor, and then the inductor will discharge back onto the capacitor, and the voltages and the current and the energy will oscillate back and forth according to sine and cosine functions. So let's play and watch that happen. And so we want to let it run through at least 1.5 periods. So notice, this is interesting, notice that the voltage across the capacitor is blue, and yet it starts at 0. And the current is red, and that starts high. So it's actually starting as if the inductor is charged, not the capacitor, contrary to the description. But anyway, if we go here, you see where the voltage is high, the current is 0, and when the current is max, the voltage is 0. And that's true at any point. When the current is high, the voltage is 0. When the voltage is high, the current is 0. And so we would write this, the red one, as a cosine function because it starts at 1. And we would write this as a sine function because it starts at 0. And the easiest way to get the period is just to use your cursor and go to the peak. Let me do that. Whoops. Go to the peak and measure the time, and then go to another peak on the blue one and measure the time, and subtract and get the length of time for one cycle. Just to check, we can go to the red trough, and then the next red trough, record the time at each one, and get the period. And there's two ways to get, we know the value of the capacitor. To get the value of the inductor, we have two different ways of doing that. One is to use the equation for the period, find that on your equation sheet, and the other is to use the energy equation. Let me show you how to look those up and see if you can find them. So by using this equation for the period, we can solve it for L. Since we have the capacitance and we just measured the period, we can calculate the inductance of the inductor. But we can check that just to make sure we measured the period right. We can use the energy equation to do this. So see if you can use the energy equation to find the inductance. Here's the equation I'm talking about. And notice 1/2 CV max squared is when all of the energy is on the capacitor. That will be when the capacitor is fully charged and there's no current in the inductor. So, but if we go a quarter cycle to where the current is max and the voltage across the capacitor is 0, then all the energy is in the inductor. And by conservation of energy, the energy when it's totally on the inductor has to be equal to the energy when it's totally on the capacitor. And since we can measure Vmax and Imax from the graph, we can use this to calculate L. It's pretty easy to do the algebra. We can multiply both sides by 2, and L will be equal to Vmax squared over I max squared times C. That's easy enough, but don't be fooled by this equation. This is when this is 0, this is at a max, and when this is 0, this is at a max. But at any other time, the energy, which is constant by conservation of energy, will be a combination of some capacitor and some inductor energy. This is just at the two extremes, but this is a very useful equation for calculating any number of things, and you will find that you'll use it both in the assignment and the lab. And that concludes our video on Lab 12.